Hello friends, in this session we are going to understand equipotential surfaces for various system of charges. Okay, so first we will find out the equipotential surface for a point charge. Okay, so we have number one, a positive point charge. Okay, so let us find out equipotential surface for a positive point charge. So we have a positive point charge over here. Okay, now let's say for example I want to find out potential at this point P, which is located at the distance r from the positive charge. What would be the potential? The potential is given by V is equal to 1 upon 4 pi epsilon naught Q upon R, right? This is nothing but the potential. So in this particular case, if you see closely, for 1 upon 4 pi epsilon naught is a constant, Q is also constant. That means V is inversely proportional to R. So that means potential decreases if R increases and potential increases if R decreases. Okay. But what if I am finding potential at every point which is located at the same distance from plus Q charge? That means if I want to, if I find out a potential which is located at again distance r, this point is a different point, but this point is also located at the same distance from positive charge. So will the potential at point Q and will the potential at point P be the same? Yes, it will be the same, right? So that means if I am joining such all such points, what will happen? Joining all such points will give me a surface at which the potential will be the same. So for this particular point charge, I require to have a surface which is in form of sphere. So imagine a sphere. So this is a three-dimensional sphere. Imagine a sphere. Now along this sphere, if you find potential at this particular point, it is located at the same distance r. So if it is located at the same distance, the potential will be the same. At this particular point, the potential will be the same. At this particular point, the potential will be the same. At this particular point, the potential will be the same. So that means we get a sphere on the surface of which, the potential remains the same. So potential at point Q will be equal to potential at point P and it will be same at every point on the surface. So this is simply nothing but what? Equipotential surface. Now if you remember the first property that we have learned in equipotential surface. What is the first property? The first property says that if a charge is made to move from one point to another point on equipotential surface, work done is equal to 0. So that means if I want to move a charge from one point to another point on equipotential surface, no work is done. How is it possible? See, let's say for example, potential at point P is Vp and potential at point Q is Vq. So, what is the equation for work done? I can say that work done is equal to the potential difference between the 2 points Vp minus Vq into the charge. Let's say for example I am placing a point charge, test charge at this point. and I am moving this test charge from Q to P or from P to Q. What will be the work done? Work done will be equal to W is equal to Vp minus Vq into V0. Right? But on for equipotential surface, Vp is equal to Vq. Potential at every point on the surface is the same. So, if Vp is equal to Vq, then W is equal to 0. So, that means no work is done while I am moving this point charge, okay, from Q to P or P to Q or from any point to any other point along the surface, along this equipotential surface will be what? 0. So, work done is 0, right? Okay. Now, the second property, do you remember the second property? What does the second property says? Second property says that electric field lines should always pass normally, should always be normal to the equipotential surface, right? So, that means electric field lines can never make an angle with the surface. It should always pass normally to the equipotential surface. Now, why is it so? Why is it compulsory? Okay, let us understand. Let's say, for example, at this point P, can you tell me what is the direction of electric field at point P? To find out the direction of electric field at point P, I am placing a test charge over here. If I place a test charge over here, will this test charge, positive test charge, get repelled? In which direction? In this direction. So, that means what is the direction of electric field? The direction of electric field is in this direction. This is the direction of electric field. Right? Is it passing normally to the surface? Yes, it is passing normally to the surface. Okay? Okay. Now, if, let's say for example, electric field is not normal to the surface, then what will happen? Let's say for example, electric field is making, I'll take this electric field over here. Let's say for example, electric field is making some angle. Let's say for example, this is the direction of electric field. Okay. Just imagine this is the direction of electric field. Then I can simply draw the components of electric field. This is the vertical component of electric field and this is nothing but what? The horizontal component of electric field. Right. So, that means the horizontal component of electric field does lie along the surface of this equipotential surface, right? If it is lying along the equipotential surface, that means there is presence of electric field over here. So, that means if I want to move the charge from this particular point to this particular point, I have to apply external force, right, against this electric field. If I am applying external force and making some displacement, I have to do work. However, work done in equipotential surface has to be equal to 0. So, that means there cannot be any electric field which is making some angle with the surface. It should always be normal to the equipotential surface. So, that means there should not be any component of electric field which is along the equipotential surface. If there is an electric field along the equipotential surface like this, then we have to do work to move the test charge against that electric field, and because of which work done will have some positive value. However, work done cannot have some positive value. It has to be what? Equal to 0. So, that means there should not be any component of electric field along the equipotential surface. That's the reason why electric field lines should always pass normally to the equipotential surface.